מה זה היה? אני חושב 7 שנים בערך. חיפשתי לעוזרת מחקר בבית גוריון, לא פה בירושלים. וחבר טוב אמר לי, הנה, יש סטודנטית שנה ג' קוראים להדר כהן, ומאז לשמחתנו, לשמחת אלון, לשמחת שמעון, לשמחתי הדר איתנו, עשתה את המאסטר, עשתה הדוקטורט שתדבר כאן. נראה לי במיוחד בתקופות האלה חשוב לציין את השמחות הקטנות, ובשבילי זו ממש שמחה אפילו גדולה, כי הדר היא בעצם הדוקטורנטית הראשונה שלי שמסיימת, בקרוב, יש לי קצת עבודה, אז בשבילי זה בהחלט יום מרגש, ואני כאן אדבר בשבחה, כי בעצם אני חושב שמשהו כאן יהיה עמוד מאחורי הקלעים, ואתם לא תראו את העבודה הטכנית הרבה שהדר עשתה, ואם יש משהו שתפיין אותה לאורך הדרך את הדר, זה שהיא ממש לא חששה להפשיל שרוולים, ולהכניס את הידיים עמוק לתוך המכשור, וכל מה שמתעסק כאן במכשור אנליטי ובפיתוח שיטות, אתה יודע כמה זה יכול להיות מתסכל וקשה, ולא רק שהדר עשתה את זה בלי שום חשש, היא עשתה את זה בעצמאות רבה, זה פשוט מאוד, עברת שני המרחים במילים האלו, אבל אני פה בצידה, וכשדברים לא הלכו, היא ניסתה שוב, וכשדברים לא הלכו, היא ניסתה שוב, עד שזה הצליח, אז זה הצליח ממש יפה. אז מעבר לזה שהיא כמובן גם עצמאית מאוד, גם מנסה להביא תמונה הוליסטית כמה שאפשר, ולהרחיב ולהעמיד. אני חושב שזה האיכויות הרבות של הדר. זה היה לי ממש תענוג גדול והלוואי, ונמשיך ככה עוד לעבוד בשנים רבות, ומקווה מאוד שתהנו.
תודה רבה. I will give the presentation in English. So first of all, thank you, Yoav, for the introduction. And so today I'm going to present you my PhD research, which is, as you have said, it is about a development of new approach for evaluating paleo-environmental conditions in sedimentary rocks, using sulfur analysis, using analytical pyrolysis for analysis of organic sulfur and pyritic sulfur, both the quantities and isotopic values of these two fractions. Thank you. On sedimentary rocks to drive some geochemical and global insights about the global cycle of sulfur. So I focused on organic sulfur and pyritic sulfur in sedimentary rocks, in organically rich sedimentary rocks. Now, when we're talking about organic matter in sedimentary rocks, the main origin comes from primary production. And the primary producers' organisms, after they die, they sink to the bottom. And along the way, they are either being consumed by other organisms or they're being oxidized. And only a small portion, about 2 to 3 per mil of the organic matter, is reaching the sediment, accumulate at the sediment, and entering the diagenesis stage. The diagenesis, the stage in which the sediments undergo lithification. And in terms of the organic matter undergo rearrangement from an individual organic compounds into one macromolecule. And eventually kerogen. So this is a general structure of this kerogen, of this organic macromolecule. And the kerogen is by far the largest organic matter pool on Earth, largest by 4 orders of magnitude than living biomass. And when it's continued to be buried with the rock, then we enter the stage which we call the catagenesis, in which the temperature are gradually increased, and the organic matter now experience high temperature, and the chemical bonds within the organic matter start to break and release hydrocarbons, bitumen, oil, and eventually natural gas. Now, kerogen, it is defined as the organic fraction that is insoluble in common organic solvent, and it consists from carbon, hydrogen, and also nitrogen, oxygen, and sulfur. So as I said, this is a general structure of the kerogen, and its structure is dependent on, first of all, the origin of the organic matter and the processes that occur during deposition and diagenesis. And usually, or very commonly, organic matter or kerogens is classified according to the atomic distribution. This is what we can see here in this diagram here, the Van Crevelen diagram. Here we can see on the x-axis the atomic ratio in the organic matter of oxygen to carbon, and on the y-axis we can see the atomic ratio of hydrogen to carbon. And what we can see is that this classification, it's basically divide the kerogen into 4 different types, and each of these types is associated by a different source. So for example, we have type 1 kerogen, which is usually, typically it is from lycostrain origin, and it's usually oil prone. And then we have kerogen type 2, which is from marine origin, and it is oil prone as well. And we have type 3 and type 4, which they both are from terrestrial origin. And only type 3 is gas prone, and type 4 is usually not prone with hydrocarbons because it is very oxidized. And this pathway that you can see here describing the thermal maturity pathway. So, for example, if the kerogen has this atomic composition, when it's released due to the temperature increase, it's released hydrocarbon, then the hydrogen content is dropping down. So this is exactly what we can see here. But today, from all this organic matter phase that I just described, today I'm going to focus on this zone from sedimentation and early diagenesis. This is a very important zone. This is where the organic matter undergoes several processes that make him leave the surface cycle and enter the geology. So organic matter preservation is basically a very important process that affects significantly on the oxidation state of the surface of the ocean and the atmosphere. It is easy to understand that if we look, for example, on the primary production equation. So photosynthesis generates organic matter and oxygen, and the oxygen is being consumed by different respiratory processes, and this small amount of organic matter that is buried and preserved, leaving an equivalent amount of oxygen in the surface. So it's so organic matter burial and preservation is an agent for the oxidation of the surface. And I'm going to zoom into this area where the sediments start to accumulate, and deeper with in the water column, and especially deeper in the sediments, oxygen become depleted. Then we can find different anaerobic respiratory processes. Among them, and the most dominant one, is microbial sulfate reduction. It is the most dominant because of the high concentration of sulfate in seawater. And in this process, basically, there are bacteria and archaeas that can use the available sulfate as an electron acceptor to conduct respiration while they oxidize the organic matter. And this process releases to the environment various types of reduced sulfur species, and I'm going to refer all these reduced sulfur species as H2S, okay, in general. And this H2S is capable of reacting with different metals, especially with iron, and precipitate pyrite mineral. And in addition, the H2S can interact with the organic compounds, the sedimentary organic compounds, creating cross-linkage between individual organic compounds and enhancing the creation of the macromolecule, enhancing the preservation of the organic matter, and in a process named abiotic sulfurization. So sulfurization, this term is referring the incorporation of sulfur into the organic matter, and this is a very important process that enhances the preservation of organic matter. And in fact, these two processes, sulfurization and pyritization, are considered competitive processes. They compete on the available H2S. And because of this relationship between the burial of organic matter and the burial and the precipitation of pyrite, so this is commonly used to reconstruct ancient redox state of the ocean and atmosphere. So here, for example, what we can see is the relationship between the buried organic carbon and the pyritic sulfur. All of this The samples here are all from recent sediments. It is all from normal marine environment, namely oxidized environment. And the use of the ratio between pyrotic sulfur to organic carbon is very commonly, the deviation of this ratio is commonly used to reconstruct ancient redox state and also to evaluate the primary productions levels. Except from quantities, isotopic values of sulfur are also very useful to reconstruct oxidation states because microbial sulfate reduction is associated by a relatively large isotopic fractionation, up to 75 per mil. And the isotopically depleted H2S that released is captured in pyrite and organic and the organic matter, recording the isotopic value. And therefore, it's also very useful. So just a few words about sulfur isotopes before we go on. So sulfur has 4 stable isotopes, and among them, the most abundant ones is sulfur with mass 32, and then sulfur with mass 34. And the delta S34 notation is referring to the ratio between the heavy isotope 34 to the light isotope 32. Now, this is an example how it is used for reconstructing ancient redox states. So what you can see here is the geological record of sulfur isotopes in sulfate and in pyrite. The 2 red lines are the sulfate, and in gray we can see the pyrite. What we can see in this area where the isotopic record, the isotopic range that pyrite record is relatively narrow, and after the great oxidation event, we can see that the range of isotopic values that pyrite record is extended, and we get another jump here in the Cambrian and Precambrian boundary. And this is attributed to the increase in sulfate availability in the ocean due to the increase in oxidation state of the ocean. It would be maybe easier to understand that if we look on a Rayleigh distillation model. So here, this is what we can see here is the Rayleigh distillation model. We can see the seawater sulfate and the light isotopic value of the generated H2S by microbial sulfate reduction and the residual heavy sulfate. And if we think on an open system, when we have high amount of sulfate that is available, then the microbial sulfate reducers can always prefer the light isotope, and then we will observe the maximum fractionation. And if we think on a closed system, then the microbial sulfate reducers must use also heavy sulfur isotope. Then we will observe a smaller fractionation, and this is attributed to what we can see here in this graph. And since this work, there has been plenty of studies that use the isotopic value of pyrite to reconstruct redox state. And in fact, the difference between the isotopic value of pyrite to sulfate is usually considered as the fractionation associated by microbial sulfate reduction, and the value itself of the pyrite is considered as the fractionation associated with microbial sulfate reduction. And here I'm asking whether the isotopic value of organic sulfur can also be used as a redox proxy. In fact, the organic sulfur is provided the 3rd largest sulfur pool. It is the 2nd pool of reduced sulfur species after pyrite, and in some places it's even the main reduced sulfur pool. For example, here in Jarib Formation, there is much more organic sulfur than there is pyrotic sulfur. And they have similar source as we saw. So this is what we can see here in this graph. We can see on the x-axis the isotopic value of pyrite relative in comparison to the isotopic value of organic sulfur. And the linear relationship between them indeed suggests that they have a shared origin. And the vast majority of organic sulfur is origin from microbial sulfate reduction and sulfurization. However, Organic sulfur is typically enriched with the heavy sulfur isotope relative to its coexisting pyrite. And usually it is thought that there is an average of 10 per mil, globally average of 10 per mil of this difference, but in fact in nature we can find different values of differences. We can find 0 difference, and we can find also 40 per mil difference between the two fractions. And it is usually thought that the isotopic record of organic sulfur and pyrite should generate parallel trend, and any deviation from this parallel trend basically suggests that there is some environmental changes, and this is how the literature is referring to this difference. And I wanted to understand what we can indicate, what exactly environmental changes we can identify using this difference. Can we see some global difference, and how can we use organic sulfur isotopic value as to help or to improve our estimation for global for past oxidation state of the surface. So to conclude this part, because we are here talking also about a new approach that include a method development, so we saw that we can study a lot from the measurement of sulfur isotopes and quantities in organic matter and pyrite. We can study the sulfur cycle, its interactions with the carbon cycle and also the iron cycle, and we can study a specific local redox state using this data. But the analysis of sulfur is also used for in petroleum industry for oil and oil source rock correlations, also to examine thermochemical sulfate reduction processes that occur during catagenesis, and it is also very useful for predicting environmental consequences due to the use of fossil fuels. So there is plenty of applications for that. So why do we need a new method? So the available method today is requiring a tedious and time-consuming wet chemistry procedure that I will describe a few slides in a few minutes. And this procedure can take several days, and it is expensive. It is because of the many steps that it requires, it's gain relatively high error. And we thought that an improved method will enhance our study for the sulfur cycle. And in contrast to sulfur analysis, organic matter is usually evaluated using a very simple method, the Rocky-Val instrument. The Rocky-Val is analytical pyrolyzer that is commonly used to evaluate the organic matter origin. It is used for petroleum industry, for rocks, for sediments, for soil, and even for plastic. It has many applications. It's very simple. It takes only 1 hour analysis. You use a small amount of samples, about 60 milligram, with minimum sample preparation, and you get plenty amount of data. Just for example, so the principle of the Rocky-Val, it has a pyrolysis oven, then followed by a combustion oven, and in each of them the temperature is gradually ramped, and the different fractions, the different carbon fractions, are eluted according to their thermal stability, and then they go to the different detectors. Here we can see an example of the thermogram during pyrolysis from the FID detector, the detector for the hydrocarbons. So we can see here 2 peaks, one for the volatile hydrocarbons and then for the induced hydrocarbons that comes from the breaking of bitumen and kerogen. And also we can identify this Tmax value, which is the temperature at maximum of the this main peak, S2. And this Tmax value is very useful parameter to evaluate the thermal maturity stage of the rock. So eventually we can calculate from that the total organic carbon, the total inorganic carbon, the Tmax value, and more parameters that are very useful. And also we can calculate the hydrogen index and the oxygen index, which are analogs to the same atomic ratio that I showed you before from the Van Krevelen diagram. And now we can, with this analysis, we can also classify the organic matter. And in my work, I based my methods development for quantification and isotopic value based on this instrument. Shimon Feinstein here and Yoav and Alon, they received from Vinci Technology, the manufacturing company, they received a prototype of the new version of the Rocky-Val before it was out for marketing. They received a prototype, and the prototype has an additional detector for a UV detector for sulfur. And I based my method on the Rocky-Val, also for the isotopic values, which we will see in a bit. So the goals of my research, the main objective, first of all, is to establish new proxies to evaluate paleo-environmental conditions using analysis of organic sulfur and pyrotic sulfur. And the intermediate goals are, first of all, to develop the method for quantification of organic sulfur and pyrotic sulfur, then to develop the method and the instrumentation for to determine the isotopic value of organic sulfur and pyrotic sulfur, and eventually to drive, this is intermediate goal number 3, to drive new proxies that can be used to evaluate diagenesis processes that are based on the sulfur and the two methods that were developed. And eventually, the last goal was to drive some new geochemical insights about the global sulfur cycle. And this is exactly how my thesis is structured. So chapter 1 and chapter 2 are devoted to the method development. And today I'm going to share with you the main results from these 2 chapters, which were already published. Then chapter 3 is considering Tmax S value, which is a new parameter that can help us understand and evaluate some processes that are occurring during diagenesis, some differences that we can see on the organic sulfur. But today I'm not going to focus in this chapter, and I'm going to show you also the main results from chapter 4, which is taking all of these 1 and 2 and 3 chapters, taking all the data I collected and driving some new insights about the global carbon sulfur cycle. And specifically, I'm looking on the competition between sulfurization to pyritization and how this competition affects the global sulfur cycle reconstruction. So, in order to develop these methods and also to drive some wide conclusions, I collected samples from different locations around the world. We can see here samples that are all considered thermally immature. It means that they are within the diagenesis stage, and they are all organically rich. But each rock sample here has different origin, different environmental origin. We have lacustrine samples, we have marine samples, and each sample here has different geology, different period, as you can see, different mineralogy matrix. And these samples, so I analyzed them for the simple Rocky-Val to gain all this carbon data, the analysis for the Rocky-Val, and also I conducted iron speciation. As you saw, the importance of iron, the importance role that iron plays in the cycle of sulfur and pyrite formation. So I also conducted iron speciation, and today I'm going to present the results of the total iron and the highly reactive iron, which is the iron fraction that is capable or to react or has reacted with H2S. And I also conducted this wet chemistry procedure. In this procedure, so this is what you can see here, this reflux system, I took the rock, and each time you dissolve it using different solvent to remove the sulfur fraction and then to capture it. So you can imagine it takes several days and sometimes several weeks. Then after I have all these subsamples and the separated sulfur fractions, so I can go offline, and to measure the quantity and the isotopic value of sulfur, I used EA-IRMS to do that. Okay, so this was the preparation, let's say, and now we'll jump into to chapter 1, which is the method development for quantification. So here you can see the calibration for the method. So we calibrated separately the pyrolysis cycle and the combustion cycle. The pyrolysis cycle was calibrated using pure organic sulfur compounds, and combustion cycle was calibrated using pure pyrite. And now I can start measure rock samples. So now what you can see here is the thermogram of a rock sample from the UV detector for sulfur. So we can see here the pyrolysis cycle, the combustion cycle, and in red what we can see is that the temperature that is gradually ramped, and we can see here several peaks. The main two peaks here are associated with the pyrolyzed organic sulfur and the pyrolyzed pyritic sulfur. However, not all the organic sulfur and the pyritic sulfur are eluted during pyrolysis, and the residual of this fraction is transferred into combustion, and it's eluted as a single peak. As you can see, there is a complete overlap between the two fractions, and in fact, this was the main challenge of the method development, both for the quantification and also for the isotopic value. We need the separation between them. For quantification, we solved it using an empirical relationship. This is what you can see here. I had these subsamples produced by the wet chemistry, and I had the organic sulfur fraction separated from all the other sulfur fraction. I was able to analyze the distribution of organic sulfur between pyrolysis to combustion, and what I saw is that it has a strong relationship with the Tmax S value, the temperature at maximum organic sulfur elution during pyrolysis, which is basically, Tmax S is basically the average thermal stability of the organic sulfur, which depends on the structure of the organic sulfur. And there is, so the chapter 3 is all about Tmax S, what we can learn from it, why we see differences between different rocks, and why it is different from the common use Tmax for carbon. But here I use this relationship as an empirical relationship to solve the separation. So if we're taking a bulk rock, we can measure the Tmax S value, and then we can calculate the relative amount of pyrolyzed organic carbon, and then simply calculate the amount of organic sulfur and the pyritic sulfur. Now I brought here a demonstration of the application of the method. What you can see here is a work from of Shawar et al. She worked on a depth profile from Jarib Formation, and she produced, using the wet chemistry I described before, she produced this profile for organic sulfur, and this is what we can see here, and this is the profile that I produced using the new method, using the Rocky-Val 7S and the empirical relationship. As you can see, we get the same, we can call it the same depth profile, that giving the same narrative in terms of paleo-environmental reconstruction. And the main differences between the two profiles is the time and effort that was spent to produce them. So for the Rocky-Val, you get 1 hour analysis. You can measure simultaneously organic sulfur and pyritic sulfur using small amount of sample, minimum sample preparation. You get a good precision, smaller than 5% relative standard deviation, and the 10% accuracy is compared to the wet chemistry that itself is associated with a high, relatively high precision or low precision. Okay, so moving on to chapter 2, which is about the development of the method for determining the isotopic value of organic sulfur and pyritic sulfur. In this part, I had to build the connection between the rocky val to the multi-collector. Now, because I did not get a separation in combustion, I only connected the pyrolysis cycle, and then I had also to examine whether there is isotopic fractionation between pyrolysis cycle to combustion cycle. But here is the connection that I built, and the main principle was to maintain as shorter as possible the way that we transfer the products from the pyrolysis to the multi-collector, and it was heated all the way in order to remain with the same thermogram, the same shape, that we can identify the peaks according to the rocky val. Here you can see the calibration. Again, I used the calibration, I used pure organic sulfur compounds that has different isotopic value, which were measured on the EA IRMS, and then we measured the ratio of the compounds. And this is what we get. So first of all, here what you can see is the same thermogram that we saw before for the, from the rocky val using the UV detector. And here alongside you can see the curves that we get from the rocky val multi-collector. So we get two additional curves, one for sulfur 34, one for sulfur 32. Then we can integrate the peak area and divide between the isotope to get the isotopic value. And because we only use pyrolysis cycle, so this one takes only 20 minutes analysis. And again, I brought the same depth profile that was produced by Shawar et al. And here we can see the depth profile of the isotopic value of pyrite and organic sulfur. And now you can see the depth profile I produced for 20 minutes analysis per sample for the same sample. So again, we get relatively good precision of half per mil, or usually lower than half per mil, and the accuracy is evaluated to up to 1 per mil compared to wet chemistry. Okay, so this was the development of the method. Now I'm moving to chapter 4. Now I have all this data, the sulfur data from the method I developed, the iron data that I added, and the carbon data from the rocky val. And now I can start to examine the interactions between the three cycles, the sulfur cycle, the carbon cycle, and the iron cycle. We can see, if we go back to our three main processes, microbial sulfate reduction, pyritization, and sulfurization. So we can see that these cycles are, we can see them here. So we have sulfur, we have the sulfate for the microbial sulfate reduction, and the H2S, and the H2S that is after that part of the pyritization and abiotic sulfurization. We also see that we need organic matter for microbial sulfate reduction, and then for sulfurization, and also iron is very important here for the precipitation of pyrite mineral. And I wanted to examine the distribution, the quantitative distribution of sulfur between the two fractions using the ratio of organic sulfur to pyritic sulfur. Also, I wanted to examine the isotopic distribution using the isotopic difference between the two fractions. And also, I wanted to examine the intensity of sulfurization, because sulfurization is, we know that is a very important agent for organic matter preservation, and I wanted to understand what enhanced the sulfurization intensity, and that's expressed as the ratio between organic sulfur to organic carbon. Now, usually in local examination, you can see some relationship between the intensity of sulfurization. This is what we can see here on the y-axis, the same organic ratio between sulfur to carbon. And the organic matter preservation, you can see this, you can see relationship in local scale. However, when we look on a global scale, it's more difficult to identify such relationship. Similarly, usually H2S availability is come in association with sulfurization intensity. We might see here some trend for the lacustrine samples, However, again, in a global perspective, it is more difficult to define such a relationship. What we can see here is we can start to see the role that iron plays in regulating sulfurization intensity, because we can see that only when iron is in low amount, we get highly sulfurized organic matter. Now, I examine the limitation of iron at the deposition environment, and this is I did using the ratio between reactive iron to the total amount of organic sulfur and pyrotic sulfur. So the total amount of organic sulfur and pyrotic sulfur are used as an indicator to evaluate the availability of H2S. And now we can start to see some global dependency. We can start to see some trends here that look similar. So here on A, what we can see is the distribution between sulfurization and pyritization. So this is the competition index. Then here we can see sulfurization intensity on the y-axis. And on C, we can see the isotopic difference. And we can here the gray line here indicates the ratio of 0.5, which is the iron limitation ratio for pyrite formation, which is calculated from the stoichiometric ratio between iron to sulfur. And we can see that the largest changes we see in this zone, the restricted iron zone, and in this zone, it is we can see a linear behavior. And what we can understand from that is, first of all, that iron play a very main role in controlling the quantity distribution. It seems that it's very important that iron will be limited in order to get highly sulfurized organic matter, and sulfurization only exceeded pyritization when iron is in a low amount, and then we get highly sulfurized organic matter. It means that on average, iron reacts faster with the H2S than the organic matter. However, it seems that probably there were also simultaneous occurrence of sulfurization parallel to pyritization, and we can see that from the isotopic difference, because when iron is in high amount, we still get some organic sulfur, and this organic sulfur record the same isotopic value as the pyrite, so they probably has recorded the same isotopic range on the Rayleigh distillation, and therefore probably they have they occurred simultaneously but in different rates. Now, trying to take all these observations and wrap it under one conceptual model based on Rayleigh distillation. So when we have low iron availability, we get preferred sulfurization, light isotopic value of pyrite, and large difference, isotopic difference between organic sulfur and pyrotic sulfur. So when we have low iron, so iron capture this very initial H2S that carry the most depleted isotopic value, and it precipitates relatively small amount of pyrite. And now there is large amount of H2S that is available for sulfurization. And of course, as I said, probably there was some sulfurization that occurred at the same time with pyritization. The other scenario, when we have high amount of, so it's high amount of iron, so we get preferred pyritization and heavy isotopic value of pyrite and small isotopic difference between the two fractions. So now iron capture a much larger range of the H2S, covers larger isotopic range of the H2S, precipitate high amount of pyrite with higher isotopic value, and there is less amount of H2S that is now available for sulfurization and result in a relatively small amount of organic sulfur. Now, this is a simple conceptual model in a closed system, and this model basically suggests that pyrite, the isotopic value of pyrite should show some relationship with the isotopic difference between pyrite and organic matter. And indeed, we can see such trends. So here what you can see, I collected from the literature isotopic data, or sulfur isotopic data of different sediment sequences, and I projected them on this graph showing the pyritic sulfur in comparison to the isotopic difference between the fractions. And we can see general trend here, and we can also see some individual trends within a specific sedimentary sequences. We can say subparallel trends. Now, there is a lot of things that probably can be added to that, but we can understand from this graph several things. First of all, it seems that the isotopic value of pyrite is dependent in microbial sulfate reduction, but also it's dependent on processes that occur after microbial sulfate reduction, such as the competition with organic matter and mainly the iron availability. And this is very important because usually pyrite, the isotopic value of pyrite, is used as the fractionation of microbial sulfate reduction. And that can be biased. It can actually mask the real isotopic fractionation, which is used to reconstruct ancient redox states. And we can also understand that large isotopic difference is usually occur in iron depleted environment, and this is very important because this is the environment that enhances sulfurization, that prefers sulfurization, which is very important for the organic matter preservation. Okay, so to conclude, the main conclusions from my work. So first of all, we have now a new method to quantify organic sulfur and pyritic sulfur very rapidly and accurately. And we have another method to determine the isotopic values of organic sulfur and pyritic sulfur. And another main conclusion is that iron plays a significant role in regulating both the quantitative and the isotopic distribution of sulfur between organic sulfur and pyritic sulfur. It also has an impact on the specific sulfurization pathway. I did not discuss about it here today, but it's an important conclusion from my work. And sulfurization is enhanced in environment where iron is depleted. And this is very important for organic matter preservation. So thank you very much for being here today. I would like to thank to all the people that somewhere or another took part in my time here. First of all, to Vinci Technology that collaborate with us in this project, and especially to Leonardo and Nicolas that gave technical support. And I would also like to thank the Ministry of Energy and the Yael Piton Foundation that giving me my PhD scholarship. And also, I would like to thank my advisors, Yoav Rosenberg and Alon Amrani. Thank you very much for all the guidance and everything. And of course, special thanks to Shimon Feinstein that I started in his laboratory, as Yoav said before, and he was there all the way. So thank you for the conversations and the guidance. Thank you very much. And of course, to all my lab mates. Some of them are here. Ilya, Chen, Yafit, Michal, Yasmin, Vasilia, Sutapa, Alex, Lubna, and Ward as well. Thank you very much.
Questions?
It's very cool stuff. So I was wondering, the samples you showed are all geologic samples, they're very old. Have you considered the effects of degradation and maybe even preference of degradation toward the pyrite or organic sulfur?
Yes.
Something that can drive some of these trends.
What type of degradation you're referring? Like?
So not kind of catagenesis, because all of these samples are obviously
yes.
Not very thermal.
So
but
I think
oxidation.
Exactly. Yes. So I think first of all, each of these samples has went through many processes, and probably sulfide oxidation was part of some of these samples, but the fact that we can still see some trends, some glows, that we can still identify something that is common for all these samples, suggesting that probably there is some connection. Now, each of these samples, the samples are so different, so I cannot tell you sample by sample what it went through. It is also very difficult and can be a PhD by itself, but the main thing here is to take like a step back and to see it all together, and we still see some global trends. So yes, but it does not mean they did not experience degradation. What I can tell you is that the fact that they all organically rich, so oxidation, I'm not sure it was very main, at least after the organic matter was buried, because it must have occurred in reduced environment. So okay, yes.
Okay. So, really great talk. I have some technical questions, like for the reactive iron is very important. How do you determine it?
The reactive iron?
Yeah.
Yes, so there is, I did not talk a lot about it, but there is the sequential wet chemistry separation, which we, each time we separate different iron fraction, and there is different minerals that considered as minerals that either has the possibility to react with H2S, or maybe they has reacted, but now they oxidize, and we measure them as oxidized minerals. For example, hematite, that is after pyrite is oxidized, you can find hematite. So yes, so it's just a sequence of minerals that you collect, and that they have different reactivities, but they're all capable of reacting with H2S.
Or reacted in the past.
Or reacted in the past, yes. So it should be our indicator to how much reactive iron was in the environment, because inreactive iron is irrelevant for this process. Yes.
And can you show again there was a lot of correlation between the isotopy measure with the IRMS and the multi-collector? Is correlation fairly?
The calibration?
Yeah. This one?
Yes, this one. So here.
So what sample is based on?
Yeah, it's based on DBT. It's all organic, pure organic sulfur compounds. D-benzothiophene, 4,6 MB, D-benzothiophene, methyl. No, it's not rock samples. Yes, the calibration of the system was a challenge, because when you calibrate, you want to use something that is similar to your samples, but we don't have any proper sulfur isotopic reference that can be examined on the rocky val. The international reference require higher temperatures that the rocky val can apply. We tried that. It didn't really work. So this is how we did it. We took pure organic sulfur compounds that we know that they are capable of be measured on the rocky val. We examined them on EA-IRMS in compared to international standard, and then we examined them on the rocky val multi-collector.
And what is the slope of the val? It's 5, or what is it?
5.5 exponent minus 5.
So it's delta versus delta? Or
Yeah, it's not delta. I made a mistake here. It's the ratio.
Okay.
Yes. Sorry.
And then doing this, can you show the next one? You got this. No, go to the next one. Maybe? Next one? Yeah.
This?
So anyway, you got this amazing correlation with the work with the...
Yes. Yes, I did not mention, but you can see that there is one point here that I did not get. There is limitation for the method. When you have a very small amount of pyrite, sometimes we cannot see pyrite peak, and then you must do the wet chemistry.